Now this is a familiar scene. These two relay technicians are performing calibration and operation tests on relays and associated circuits. They are working under a work permit, and line 301 has been isolated for this purpose by the operators. So there is no possibility of any impact on security of the system during this test, is there? But hold on now. What's happening here? Look, the bus protection has operated and cleared the bus, including the generator. Disaster, an outage, and interruption to customers. So what caused this inadvertent trip? Well, something has obviously become crisscrossed at some point. Perhaps the technician, by mistake, is working on the wrong circuit. Let's look at another case. In this particular control center, the system operator is advised that a big storm is brewing in the mountains. He knows from experience that under these conditions, line 62 is liable to be cleared by ground fault protection as a result of lightning. He also feels confident that the rest of the system is secure and can handle this outage without jeopardizing system integrity. Sure enough, there goes line 62, tripped at each end by ground protection. But look, line 61 has tripped, and lines 64 and 73 have tripped as far back as the generator substation. Apparently, some misoperation in the protection equipment has caused overtrip, with the consequent interruption in service to customers. Unfortunately, it is a fact of life that inadvertent trips and misoperations do occur on power systems. Even though this is a subject which we often put at the back of our minds, we're now going to open up and discuss this very serious problem for the next hour on this videotape. We'll be looking at some of the prime causes of inadvertent trips and misoperations and see what we can do to reduce the potential for this. The term inadvertent trip generally refers to an error by employees while working around power company equipment. Misoperation, on the other hand, refers to a failure of the protection scheme to operate correctly, even though the original cause may be due to incorrect wiring or other human error. Right away, let me point out that the actual number of such occurrences in any particular power company are usually very low, say 2 to 3 incidents in any one year. Of course, there are bound to be some years that suffer more such incidents. To give you some idea of the trend of the problem in your organization, check your own company statistics for the past 10 years. However, even 2 or 3 inadvertent trips are too many, and we must do all in our power to eliminate such occurrences altogether. There are several main causes of inadvertent trips and misoperation that immediately come to mind. Communication errors, people getting different meanings from the same message. Human error, as indicated in our first example. Protection equipment failure under actual operating conditions, our second example. Poor design, inaccurate schematics and wiring diagrams, mistakes in wiring, incorrect labeling and identification of equipment, faulty equipment from the manufacturer, incorrect relay setting. Note that most of these items are a result of human error somewhere in the chain. For example, incorrect wiring, poor design, incorrect relay setting, and so on. The most common causes of human error are lack of attention to detail, not being fully prepared for the job, taking shortcuts, making assumptions, especially on routine jobs, and not following procedures. Clearly, there are many potential areas where errors can creep into the protection scheme, and much of this can occur during the installation stage. This could be during construction of a completely new facility or perhaps modification of an existing station. In order to help us study this subject, we are going to look at a few examples of actual occurrences. Yes, these incidents really did happen. In fact, some of you may recognize the case studies from your own company's files. Please pay close attention to the details of these case histories. By realizing what went wrong, we should be able to come up with a few ideas on how to eliminate or at least reduce the occurrence of inadvertent trips on the system. So here is our first example. The ground fault protection on this line consists of an instantaneous time over current relay supervised by a directional unit. When a heavy ground fault occurred on one phase of this transmission line, the directional ground over current protection failed to operate. The fault was actually cleared by other protection. Subsequent checking of this scheme showed that the instantaneous relay picked up correctly, but tripping was blocked by the directional unit even though the current was in the operate direction. Further checking revealed that the documentation provided by the relay manufacturer indicated wrong voltage connections for the polarizing circuit, and the directional element was wired this way. As a result, the relay blocked the instantaneous relay from tripping for faults in the operate direction. By the same token, it allowed tripping for faults in the non-operate direction. The manufacturer was informed, the diagrams changed, and the connections corrected. After this, simulation tests were performed and the protection operated correctly to trip for faults in the operate direction. This was expected. However, what was not expected was that for faults in the reverse direction, the directional elements still allowed false tripping to occur when it should have acted to prevent operation. Further detailed testing showed the reason for this. When a fault occurs, the instantaneous relay picks up in 8 milliseconds. But with pre-fault power in the operate direction, the directional unit takes 26 milliseconds to sense the change in direction of power flow. Consequently, the blocking from the directional unit is too late to prevent the instantaneous relay from tripping the line. This misoperation is due to several causes. First, the wiring was incorrect. This should have been detected by in-service load tests during the commissioning stage, even though the manufacturer's information itself was incorrect. So we have manufacturer's error. We also have a design error because this particular combination of directional unit and instantaneous unit allowed false tripping. Apparently, this installation needs a faster directional unit. Now let's take a look at another example. In this installation, a lightning arrestor failed, resulting in a ground on one phase of the 345 kV bus. Note that at the time this bus section breaker 6W was open, with the station operating as a split bus. Under this configuration, we would expect the bus fault to trip breaker 5W on the faulted side of the bus. This is in fact what happened, thus isolating line 68. However, breaker 4W also opened, isolating transmission line number 62. This trip was not correct. Subsequent investigation proved that one of the relays in the circuit had been wired incorrectly. Once again, an error that apparently slipped through the commissioning tests. The wiring was subsequently corrected and the relay placed back in service. But this was not the only problem during this fault incident. When a fault occurs at any point, it is detected by other protection schemes throughout the system. However, as we know, the protection schemes are coordinated to provide selectivity so that only the faulty section is cleared. Unfortunately, this did not happen in this case. Breaker 7W opened inadvertently, clearing line 42 and all associated breakers along the line due to transfer tripping. Once again, investigation showed that the ground fault detector relay at this point was incorrectly wired. There is more yet. As a result of the bus fault at Station A, this interconnector way out here tripped at both ends. Testing of the directional comparison relay system showed that the equipment was functioning correctly. However, it was determined that the relays in this scheme had been set to overreach too far. They have now been reset to a less sensitive value. Once again, we see the problem here of incorrect wiring and incorrect setting of relays. These problems should likely have been picked up during the commissioning and acceptance tests of the equipment. Clearly, it is essential that such tests be performed after any installation work has been carried out. Another problem is that this defect would not have been discovered if the fault had not occurred. We know that faults are very rare, and some protection equipment has never actually operated under true fault conditions. This is the reason that routine testing of every protection scheme must be carried out at regular intervals. Even though routine tests are less detailed than commissioning tests, we would expect to detect installation defects that may have been missed during commissioning. Just as important, routine testing will also reveal problems that may have arisen during operation. Now, our next study shows a defect which could not go undetected. This generator was being returned to service after an extended outage for modifications. As soon as the generator was synchronized to the system, the differential relay operated and tripped the unit. During the modifications, the generator CTs had been removed so as to allow changes to be made to the generator support structure. The investigation showed that upon reinstallation, the B phase line side CT was wired backwards. The drawings and markings were correct, but the electrician made a mistake when connecting up. As in the previous cases, this shows how vitally important it is that all wiring be thoroughly checked after any modifications or installation work has taken place. Perhaps the unit was required back online in a hurry. Does that sound familiar to you? Your company's procedures will include standard instructions for testing and commissioning new installations or modifications to existing equipment. The standard procedures of different companies may vary in detail, but in general, they must cover the same ground, as, after all, they have the same objective. The first item mentioned in the procedures is usually that of safety. This is a reminder to the technician to be aware of potential dangers associated with commissioning tests. The next item is a physical inspection of the protection equipment to make sure that equipment supplied by a manufacturer does in fact conform to the bill of material. Also, make sure that the manufacturer has supplied the correct instruction manuals, test reports, and other documentation pertaining to the specific equipment. While checking the installation, a visual and mechanical inspection should be made of every item of equipment. This means looking out for loose parts, loose connections, shorted terminal lugs, broken glass, foreign material, and so on. Having completed the mechanical inspection, complete electrical tests must be carried out. As preparation for this, we should already have checked that the wiring diagrams conform to the schematics. This can often save us a lot of time in tracking down problems later. On new installations, all of the wiring must be checked to see that it conforms with the diagrams. Point-to-point continuity and insulation integrity must be checked on all AC wiring, from switchyard terminal blocks to the termination points in the control panel. Typically, this will include breaker control cables, differential junction boxes, CT and VT leads, line tuners, and so on. We must also check that components mounted on the panel by the manufacturer coincide with those shown on the elementary diagrams. This includes such items as resistors, capacitors, diodes, transformers, and various switches. This checking out of the wiring may well be tedious, but it is clearly necessary in order to avoid problems such as discussed in our earlier examples. After the wiring checks have been completed successfully, we're ready to look more closely at the protection scheme. First, the relays must be calibrated and set according to instructions. After calibration, the complete protection scheme must be checked for operation by simulating fault conditions. As we noted in earlier tapes, this is done by injecting controlled values of current into relay primary and secondary circuits. This will verify that the total scheme, from fault detection through to breaker tripping, is functioning correctly. All of this must be carried out before the new installation is energized. However, further in-service load tests are required as soon as the equipment is placed online. This is because power flow is necessary to enable us to check the proper phasing of directional relays. Also, differential protection schemes are checked at light load to make sure that voltage and current measurements are balanced and correct for the intended relay functions. If you use a multimeter to check voltage sources at relays, make sure that it is not set on the amps range, otherwise it will short the voltage and trip the relay. We have been looking at a broad overview of commissioning tests. Make sure that you become familiar with your own company's procedures. Conscientiously performed, commissioning tests should bring to light problems such as faulty or incorrect manufacturer's equipment, incorrect wiring diagrams or schematics, incorrect wiring, faulty protection scheme design, incorrect CT and VT connections for differential and directional relays. Detecting these problems right at the beginning will certainly reduce the need for troubleshooting later. More importantly, it will provide the relay protection required to ensure system integrity. Now, at this point, let's take a break, and then we'll come back and talk about routine tests of protection schemes at standard periodic intervals. For now, switch off the tape and thoroughly review this material in your workbook. The incidence of faults on the power system is in fact quite rare. Now, I know it doesn't seem this way when we're called out to attend various problems during a heavy storm, but it is true that most of the protection equipment is rarely called upon to operate to clear a fault. And yet, when a protection scheme is required, it is vital that it operate reliably with perfect sensitivity and selectivity. I suppose it's inevitable that this perfect world cannot exist 100% of the time. And misoperation does in fact take place due to protection scheme failure. Let's look at a few case histories of this. In this sample, line 11 developed a ground fault, and this was cleared correctly by tripping the breakers at both ends of the line. However, what was not correct was the tripping of the number 6 generator. This misoperation trip was triggered by operation of the generator ground directional overcurrent relay. Subsequent investigation of this relay showed that a capacitor in the voltage polarizing circuit had failed. So the relay, in effect, had lost its sense of direction. Now, we don't know whether the capacitor failed at this particular fault occurrence, or perhaps the relay had been sitting in this ineffective condition for some period of time. If the fault had not occurred, the problem with the capacitor would no doubt have been discovered only during the next routine test. Let's look at another example. In this system, a ground fault developed on this line due to a failed lightning arrestor. The line cleared correctly by operation of the directional ground carrier protection scheme and also the directional ground overcurrent instantaneous relay. But look, out here we also have a breaker trip, and this is incorrect for an external fault. Investigation showed that this breaker failed to receive the blocking signal over the carrier system. The problem was due to a failed wave trap, so that the signal was lost. This wave trap was replaced and the system put back into service. Once again, this faulty wave trap and associated carrier system may have remained inoperative for some period of time until discovered at the next routine test. Of course, we could show many more examples of this type of problem, but it is fairly obvious that not all protection equipment stays in its as-new condition. Small items of equipment wear out. Settings may drift in certain instances. Stray ground currents may infiltrate the circuit. Insulation may deteriorate, and so on. For this reason, it is essential that routine testing of protection schemes be carried out at standard intervals of time. In most companies, the time period is every 2 years for 115 kV systems and above, and every 4 years for lower voltage systems. Now, we know that the system operator or station operator does not like to see the relay technician turn up with his test equipment to disturb the status quo. But he knows as well as you and I that routine testing of protection equipment is vital to ensure that it really does operate when needed and that it does not misoperate at other times. However, the tester must be on his toes and take all precautions to ensure that he does not cause inadvertent tripping himself while conducting the tests. Before he even enters the station, he must be aware of the high voltage configuration. Is any equipment out of service? He must scope out the job beforehand and determine the possible impact of an inadvertent trip. You really have to know what you're doing and practice extra caution continuously. Good cooperation between the operator and relay technician is vital, especially during the preparation stage for testing. Be sure to let the operator know the extent of your tests and the time period. It is to be hoped that the equipment under test can be taken out of service and isolated so that the tester's activities will not impact system operation. However, this may not be so easy, because in many schemes, protection on the isolated circuit may have some interconnection with a protection scheme on a neighboring live circuit. In this situation, special precautions must be taken by the relay technician to prevent interference with the live circuit. He must also alert the operator to any possible problem conditions that could arise, even remotely, so that the operator can prepare some contingency plan. The operator should also be informed of the time which will be required for the tester to abandon the tests, disconnect his test equipment, and make the line available in case of emergency. With certain items of equipment, it may not be possible to arrange an outage, and in this case, the routine testing of protection schemes will have to be carried out on live equipment. The subject of in-service tests will be discussed in detail in the following segment. So let us consider that our tester has received a work permit and the circuit under test is isolated at his disposal. What tests will he perform? Well, your company will have very detailed procedures laid out for testing all of the different types of relays and protection schemes on your system. You must have access to these procedures and use them when performing any tests. In general, the procedures cover the following areas. First, a general warning about safety. One item, for example, is the need to look out for open-circuited CT secondaries. Attention is drawn to test instruments. Usually, a list is provided according to the particular type of protection scheme. One important point here is that test instruments must be calibrated and be of a level of sensitivity and accuracy which is higher than the tolerance permitted on the equipment under test. The first part of the test consists of the visual and mechanical inspection of all components, including wiring. Check connections for tightness and look out for insulation damage and the presence of dirt or oil. Prior to calibrating the relay, the as-found settings and general condition are noted in the test records. Calibration of each relay must be carried out in accordance with the manufacturer's instructions and specific company operating procedures. Usually, a sufficient number of calibration points are checked so as to verify the characteristics of the relay. For example, the time over current characteristic of an overcurrent relay. As soon as the calibration tests are completed, operational tests should be performed to make sure that the desired breakers actually trip for relay operation. The breakers would, of course, be isolated from the power system by disconnects. But even so, this operation should be coordinated with the system operator. Once this test has assured that the breaker trips from the auxiliary relay, further testing of protective packages can be performed by isolating the breaker trip circuit and verifying operation of the auxiliary relay only. This method will reduce wear and tear on the breaker. If an automatic reclosing relay is installed on this circuit, this must also be tested for operation at this time. The reclosing relay should be tested for each of its different program functions, that is, its different time settings. Operational tests should also include the sending and receiving of appropriate communication signals for pilot schemes or direct transfer trip. All of the results from calibration and operational testing of the various protection devices must be clearly marked on the test record sheets. At the completion of the tests, all relay targets, annunciators, and alarms should be reset. Also, all test switches, sliding links, and so on must be returned to the appropriate position. Similarly, remove all test fixtures, leads, plugs, jacks, etc., and restore the equipment to its normal operational condition. Where appropriate, remember to connect the relay restraining contacts first, wait for it to stabilize, then connect its operating circuits next, wait for it to settle down, and finally cut in the trip circuit. Similarly, when replacing an under-voltage relay, insert the connecting plug very slowly so that the long fingers contact first, or hold the contacts open to block false operation. Inadvertent tripping can and does occur during routine tests. Let's look at an actual incident. The two technicians were performing tests on this isolated feeder number 89. They had a permit to work and were proceeding to test the carrier and associated equipment. One technician located at the carrier equipment panel initiated a blocking signal and signaled to his companion at the relay panel to operate the lockout relay so to stop the blocking signal. However, in order to improve communication between them, this fellow moved his position just slightly, but enough to cause him to operate the relay on the adjacent panel. As a result, feeder number 50 tripped. Realizing what they had done, the technicians immediately informed the operator, and the feeder was restored within minutes. The point here is that even though the circuit under test may be isolated, there is always the possibility of in-service equipment being disturbed. Now you can understand why the operators would rather not see relay technicians with their test equipment. It is most important that all of these incidents of inadvertent tripping be reported and thoroughly investigated. Don't try to cover up. A written incident report should then be circulated so that all interested parties can learn from the experience. In most companies, incident reports are also prepared for misoperation due to operator error or other maintenance technicians, electricians, and mechanics. Here is another incident. This breaker number 52 was under maintenance by electricians. The two disconnects on either side were open, and the bypass switch was also open. One of the electricians out in the yard called and asked the relay technician, who was working on the control house panel, to try and close the breaker for the maintenance crew. Remember, it was isolated. In fact, the technician got hold of the wrong handle and closed the bypass switch instead. At the instant of contact, the bus differential protection operated and cleared the whole bus. Once again, a case of mistaken identity. And here is yet another. In this case, feeder number 21 was isolated for maintenance. The relay technicians needed to perform circulating current tests on the CTs associated with the isolated line. The CT terminal blocks were located in the breaker number 1 control cabinet. The technicians left the relay house and opened the panel door at the nearest breaker. As it turned out, this was actually breaker number 3, and when they applied the test leads, the breaker tripped. A transfer trip was sent to the remote end of the line. As a result of this inadvertent trip, the remote generator was no longer in service. The breaker panel was clearly marked number 3, but the technicians had been misled by using a schematic diagram which showed the number 1 panel to be located close to the relay house. Here, then, is the nub of the problem. First, they should have been utilizing the physical wiring diagrams which actually show the true geographic layout. Also, all of us must always check the identification of any equipment on which we intend to work. One problem is the relay technician is in a somewhat vulnerable position. Even the tiniest mistake cannot go unnoticed. But after all, that's one of the challenges of the job. That's why we have to be professional in everything we do. Take extra care, study details, check and double check, and don't take shortcuts. Where in-service testing is involved, the challenge is even greater. And we'll be talking about this in the next segment. For now, please switch off the tape and review this material in your workbook. We already pointed out in the last segment that some items of equipment, high-voltage transmission lines, for example, cannot always be taken out of service to permit routine testing of protective equipment. But we still need to carry out the testing to assure that the protection schemes will operate correctly when needed. In this case, we have to carry out the tests with the line in service carrying load. Now we're coming to the real nitty-gritty. The potential for inadvertent tripping under these conditions is quite high. One false move by the relay technician and he will trip out the very line that he is trying to keep in service. It is ironic that by performing the tests to ensure that protection equipment will not cause incorrect tripping, we run the possible risk of inadvertent tripping during the very test itself. In-service testing may also be required at times other than routine testing, for example, during troubleshooting. In-service tests are also performed to measure current and voltage on relays during normal operation. This serves as a check on the measuring circuits, CTs, and VTs. As the technician must access live relays, we have to face the possibility of inadvertent tripping. Clearly, great attention must be paid to both preparation and performance of in-service tests. Most companies lay down guidelines and procedures to cover this activity. The major issue is that as the line remains in service, it must continue to have some protection equipment still operable. Frequently, high-voltage transmission lines are equipped with duplicate protection schemes, including duplicate CTs and duplicate tripping coils in the breaker cabinets. In this situation, one complete set of protection can be removed for testing while the other package remains in service. Even with this arrangement, testing will be conducted with the least number of relaying components out of service at any one time. Many pilot relaying schemes include duplicate communication channels. This enables the technician to remove one channel at a time for testing, while the line remains in service protected by the single channel. On lower voltage systems where duplicate protection is not provided, we have to rely upon alternate protection to clear any fault while we disconnect one relay at a time for testing. In fact, the ability to perform in-service testing should be taken into consideration during the design of the system protection. Before commencing any tests, the relay technician must discuss the scope of the work to be performed with the operator. They will jointly review the work plan along with the high-voltage operating diagram to determine if the test can be performed safely. The operator should also be alerted to the potential for defined inadvertent tripping during the in-service tests. This will allow the operator to prepare a contingency plan. He may also wish to inform interconnected neighboring utilities. In most companies, in-service testing is not allowed during peak load or during storm conditions and storm warnings. Also, the permit to work is issued on the understanding that the isolated protection system can be restored to service within 30 minutes' notice. We certainly need all the protection we can get when abnormal conditions occur on the system. In-service tests usually take two forms. One is to check the inputs to relays from CTs and VTs. This is to ensure that the sensing circuits are functioning correctly. Secondly, it is necessary to test the relays themselves for operation. Because the line is still in service, it is essential to disconnect the relay output so that actual tripping will not take place. Remember, we cannot disable the tripping circuit at the breaker because this is still in service and must be able to trip from other sources. The relay output may be isolated by switches, sliding links, or test plugs which are provided for this purpose. In some cases, there may be no alternative but to disconnect wires. In performing the tests, there are many other precautions that must be taken, but before we look at these, let's first view some case histories and learn about some recurring problems. In this case, two technicians were calibrating and testing the bus protection scheme. The test was carried out with the bus energized and the primary differential protection scheme isolated. The redundant backup differential protection scheme remained in service to protect the live bus. As part of the test, one pair of contacts was jumpered and another pair was manually closed. It turned out that these were the wrong contacts, and this led to operation of the redundant differential scheme and so tripped the bus. As in many cases, both of the differential schemes are presented on the same diagram, and it is certainly possible to look at the wrong numbers if great care is not taken. Now, here is another example, and this is actually quite a common problem. This technician was working on live equipment to perform in-service tests. He was removing the cover of the directional overcurrent relay, which is located right at the bottom of the panel. The technician had to squat to remove the relay cover. While doing this, the target reset lever on the cover became misaligned, allowing it to mechanically lift the target seal-in contacts, causing the trip circuit to operate. Many such incidents have occurred both during installation and removal of covers. I suppose that by now we should have expected that the design of the relay itself would eliminate this problem. But of course, we still have many of these relays out there. Another variation of this problem occurred when the relay cover was not put on properly. It caused the contact to partially close, and then when the cover was removed at the next routine inspection, the slight movement caused the reset lever to bridge and trip the circuit. This problem could have been eliminated by isolating the relay tripping circuits before removing the cover. But this is not always so easy. One relay technician trying to resolve this problem elected first to disconnect the downstream auxiliary relay coils. He managed to disconnect 3 of the coils, but at that point the remaining coil operated and tripped the circuit. So how did this happen? Well, in this arrangement, we have one indicating lamp in series with these 4 coils in parallel. There is also a resistor across the coils. This resistor was found to be open-circuited. Now, as each of the coils were opened, the voltage across the remaining coils increased. Remember, these are in series with the indicating circuit. Eventually, as the 3rd coil was disconnected, the voltage across the remaining coil rose sufficiently to operate the relay and trip the breaker. The 4 auxiliary relays have now been replaced with one multi-contact relay. And here is another case involving relay covers, but with a difference. One relay technician was working in front of the panel while his companion was behind, observing operation of the relays. Within the vicinity, there were several live relays without covers, and he inadvertently brushed against one of these, causing tripping of a bus section. It is true that the technician should have taken more care, especially as protective covers were not on all the relays. But these relays were not part of the test. They had probably been in this condition for some period of time. Additional wiring had been added some time ago, and this prevented the cover from being replaced at that time. Clearly, special covers should have been made to fit the new situation. Relays should always have covers in place when in operation. Apart from the possibility of inadvertent operation, there is the likelihood of dirt and moisture getting into the relay components. And here is another interesting case. 2 technicians were involved in replacing 2 ammeters on a live transformer. Each ammeter formed part of the differential protection circuit. The objective was to bypass the ammeters with jumpers, remove and replace the ammeters, and then remove the jumpers. Jumpers with alligator clips were used. As soon as the work commenced, the transformer tripped on differential. It appears likely that one of the alligator clips became disconnected, and so energized the differential protection circuit. There is another possibility. It was noticed that one of the technicians was wearing a large bunch of keys on his belt. Perhaps these keys breached contacts on the CT terminal block. This draws our attention to the well-known basic rule that metallic objects, such as rings, keychains, pocket tools, watch bands, and so on, should not be worn when working in the vicinity of live circuits. Also, we should not use jumpers with alligator clips when we are working on current circuits which are in service. A jumper must be used that can be positively secured to a screw connection on a terminal post. In this way, it cannot be accidentally knocked off. Well, are you tired yet of these dismal stories? Let's look at just a couple more before we stop to draw some conclusions. In this particular occasion, a relay technician was performing in-service tests on a 133 kV line. This relay has a flexi-test switch mounted below. The technician removed the flexi-test switch cover and was preparing to insert the test jack into one current circuit. He then, by mistake, opened the wrong flexi-test switch. This caused an unbalanced condition in the relay, which consequently operated and tripped the breakers. The main problem here is that they had failed to isolate the trip circuits from the relay before commencing the test. In fact, it is usually established relay test practice to isolate trip circuits as soon as the relay cover is removed. Moreover, this particular relay has a red warning sign placed directly over the flexi-test switch. It says, "Stop. Isolate trips before opening." In spite of this, the technician went ahead and caused the inadvertent trip. Here's another incident with a similar cause. The technician was testing relays on transformer number 2, which had been isolated. However, some of the relays on this panel are interconnected with other protection circuits, such as bus protection. For this reason, the technician attempted to isolate the trip wires from the differential relays. However, the wrench he used was not suitable, so he could not remove the terminal nuts. Instead of looking for another tool, he looked at the diagram to trace the trip wires to the next connecting block. He could not find this connecting block on the relay panel, so he decided to alter his test procedure. He assumed that the isolation test device had actually isolated all trips from the relays. So with this assumption, he connected the test leads to the relay and applied pickup current. The resultant operation of the differential relay inadvertently tripped several other breakers on the bus. This instance shows the problem of taking shortcuts. We know that this may be done in good faith in order to save time and get the job done. But in this particular case, it would have been better if our technician had looked for the correct tool and removed the trip wires from the relay before proceeding. So what have we learned from all this? Well, clearly there are several common conclusions resulting from these inadvertent trip incidents which occurred during in-service testing. One of these we have just looked at. That is the absolute necessity to isolate the trip circuits from the relay being tested. This should be done as soon as the relay cover is removed or before, if this is possible. Another problem is due to physical movement around this highly delicate equipment. Opening swing panels and removal of relay covers always requires care and attention. Make sure that you have the right tools. Alligator clips are a no-no on live current circuits. Also, and I am sure I have no need to repeat this, never wear metallic objects while you're working on live equipment. Identification of equipment is vital. You must always make sure that you are working on the right equipment and that this corresponds to the schematics and diagrams. Good work planning is vital so that you know precisely what needs to be done and how to go about it. Most companies require that the technicians fill in a job procedure form before commencing work. This includes the objective of the work, isolations required, and each of the major steps to be performed. Always check and double-check all panel and relay nameplates before starting work on a relay. It is also a good idea to tag all adjacent equipment that is not to be operated. Perhaps your company does this the other way around. When you are taking in-service load readings, be careful to check if any additional circuits may be affected. For example, an unbalanced phase relay may possibly cause an associated ground relay to operate. Before commencing work, take note of the as-found position of all test switches. On completion of your work, they must be returned to the original position. Communication is important with operators and also with your own group. This is especially so when performing any critical operation, such as tests of transfer trips or breaker failure schemes. Make sure that messages are clear with no chance for misunderstanding. Try not to use local jargon that may not be understood by other departments, and particularly by other utilities. By far the most important point is for you to be on your toes, follow procedures carefully, know your job thoroughly, and carry it out professionally. All right, so far we've looked at commissioning tests, periodic routine tests, and in-service tests, all aimed at improving the reliability of protection schemes and reducing, if not eliminating, the incidence of inadvertent tripping and misoperation. But the relay technician is also called in to troubleshoot after misoperation of the protection equipment. We'll have a brief look at this in the next segment. For now, please switch off the tape and review this material in your workbook. Up to this point, we've been dealing with pre-planned inspection and testing of protection equipment. But relay technicians are often called in to investigate trouble. A trouble call to a relay technician will usually be the result of an alarm or a system fault or misoperation of protection equipment. When answering one of these calls, the first thing you should do is to review the events that occurred, such as open breakers, relay targets, annunciator indications, and so on. Make sure that these indications are correctly recorded, especially relay targets. If the fault involved station equipment, such as a bus or transformer bank, this should be visually inspected. The investigator should be able to evaluate the extent of the problem and decide which, if any, equipment isolations are required. In order to verify the cause of misoperation, it will be necessary to check relay calibration and the operation of interconnected equipment in the appropriate control scheme. This will involve checking wiring, auxiliary relays, measuring relays, CTs, VTs, and perhaps even a circuit breaker. Problems are usually traced by a systematic isolation of each path and associated components. Faulty components will have to be replaced and the protection relays recalibrated if necessary. When investigating the cause of the problem, it is most useful to go through station oscillograph records and the printout from the events recorder. It may even be necessary to collect and view the records from other substations around the system. On completion of the investigation, all relay targets, annunciators, and alarms must be reset, all test equipment removed, and the equipment returned to as normal condition. If items need to remain isolated due to defect, then this equipment must be properly tagged and the appropriate departments notified. Let's look at a few case histories of misoperation that resulted in a trouble call to relay technicians. A serious outage occurred at the Port Jervis substation. Line 11, Line 18, and Line 10 all tripped inadvertently due to operation of HZ and KD relays. Investigation showed that at the time of the trip, electricians had taken out a permit to work on switches 7 and 8 here. When the switches were both opened, the potential transformer became de-energized. As a consequence, the relays lost potential restraint and operated. The correct procedure would have been for the electricians to open one switch at a time. It is probable that neither the electricians nor the operators were looking for problems with VTs or CTs when they planned the operation. It is usually only relay technicians who think about these things. Another case of a trouble call is shown here. The task was to discover why breaker 1320 tripped for a fault on the other line. In fact, the faulted line cleared correctly. Both breakers opened, as well as the breaker on the transformer tap. These were cleared by directional ground carrier protection. However, breaker 1320 should not have operated for a fault outside of its zone. This breaker was tripped by phase comparison carrier protection. The investigation showed that the blocking signal was not sent from the other end of the line, and the reason for this was that the test switch had not been properly reset to the on position, presumably since last testing. In this case, in order to avoid a repeat, the test switch contact was removed from both ends of the line. Here is another interesting example of a type of problem that could confront any one of us. Two technicians were sent out to the substation to verify some modifications which had been made to protection wiring. At this time, breakers 1, 2, and 6 were open, leaving only this section of the bus in operation. Generator number 3 here was supplying feeder 21 and also supplying the feed to substation B. The technician's task was to verify modifications which had already been made to the existing breaker failure relaying for breaker 2. Specifically, they had to check that the breaker failure timer and an associated lockout relay were out of service, and that the output circuits were disconnected. The task looks simple enough. Breakers 2 and 1 were already open, so all they needed to do was to trip the lockout relay and verify no operation of breaker 1 trip circuit. However, when they went to the relay panel, they found that all of the relay circuit designation tags had been removed. This included the 2 lockout relays, one associated with the breaker 2 failure and the other with breaker 6 failure. So the question arose, which one of these 2 lockout relays should they operate? Because the circuit tags had been removed, the technicians began to think that both lockout relays had been disconnected. After all, this was the eventual plan. Moreover, standard practice in this company was to remove circuit tags from disconnected circuits. When they reviewed the construction schematics, this did indeed indicate that both lockouts were out of service with their output wiring disconnected. These schematics were actually drawn to show the eventual final circuitry after modification. Just to make another check, they looked at the physical wiring diagrams for the panel. But by this time, they had already convinced themselves that both lockout relays were out of service. In fact, they failed to recognize that the wiring diagrams actually showed the physical location of each lockout relay. It also indicated that the lockout for breaker number 6 was not yet disconnected. Presumably, this would be carried out at a future operation. So the technicians decided to take a shortcut and trip both lockout relays in order to prove no breaker operation. First, they arbitrarily chose one of the lockout relays. This proved to be the one that should trip breaker 1. Of course, breaker 1 did not trip, as this had been disconnected. They should have stopped right there while the going was good. However, they then moved on to trip the lockout relay associated with breaker 6. The result was an inadvertent trip of breaker number 5, which caused an outage on the feeder to substation B. Now the technicians knew or should have known that breaker 5 was in service and that tripping the lockout relay may indeed trip that breaker. They should have stopped the actual testing and investigated further until they could have positively identified the lockouts and verified that the wiring really was disconnected or not. Now, in this example, there are several lessons for all of us to learn. First, be prepared. This means a thorough review of the task before you start. Know what could result from your actions. Pay attention to the details. Check all diagrams and schematics and call on any other resources which may be required. Always follow procedures. Don't take shortcuts. Even stop the job if you have to. Don't assume anything. When something's not going as we originally planned, and this is quite often, we become most vulnerable to making mistakes. Always stay alert and concentrate on the assignment. Plan for the unexpected. Continually ask, what if? Always be aware of the possibility of an inadvertent trip. make the time to take the necessary precautions and care. Now, please don't get depressed about all of these mistakes that we've been looking at. As we said earlier, these are really very few and far between. We are not mentioning here the many hundreds of tests and other assignments which are carried out by relay technicians without the slightest problem whatsoever. Nevertheless, we must do all we can to reduce inadvertent trips to a minimum. When they do occur, make sure that the incident is thoroughly investigated and reported, and the information circulated to all interested parties. These reports are usually circulated also to neighboring utilities so that the experience can be shared by all. In this way, we should learn how to continuously improve our testing procedures, protection design, and even how to keep on top of manufacturers. Make sure that you discuss this subject of inadvertent trips with your own colleagues and supervisors. This is a vital subject that needs continuous interchange and communication between us all. Please switch off the tape now and review this material in your workbook.